So this section is called in-program data gathering, and it basically shows you how to start and stop gathering within a program. So data gathering, as Alex explained earlier, can be configured through the plot program, where you select which quantities to gather and at what speed, but he probably didn't teach you how to actually start and stop within a program. So within a program, we can use the gather.enable structure to turn on and off gathering in different ways. So gather.enable equals 3 will gather indefinitely, which means it will fill up your available memory with gathered points and then roll over once it runs out of memory. I don't recommend using gather.enable equals 3 from a motion program because that can sometimes break the plot program. The plot program will actually turn on gather.enable equals 3, I believe. But if you do it from a program, it gets a little bit confused. So from a program, you should almost always use gather.enable equals 2, which will gather only up to the buffer size that you've configured through the plot program, and then stop once it reaches the end of the buffer size. Excuse me. Gather.enable equals 1 will stop gathering and leave the gather pointer at the end of the buffer. There's really no point in doing that, so I don't use that. And gather.enable equals 0 will stop gathering and reset the gather pointer to the beginning of the buffer. This is basically what you use every time you want to stop gathering. So let's look at some examples. This is just a motion program. Doesn't really matter what the motion program is doing, but the main point of this example is you have, after you set up your motion parameters, you put a dwell 0, gather.enable equals 2, dwell 0. Whenever you have a gather.enable command in a motion program, you need to encapsulate it in dwell zeros. That way it'll start gathering exactly at that spot in the program. You can't use synchronous variable assignment with gather.enable. Normally you'd be able to do the double equal to thing, but it doesn't work for gather.enable. I've tested it. And then right after you do gather.enable equals 2, dwell 0, you can execute your relevant motion, and then at the end of the program, you have some form of dwell, gather.enable equals 0, and then there actually should be a dwell 0 at the end here for robustness. And then through your plot program, you can, if you've already set up your gathering settings, the quantities you want to gather and so forth, you can just upload the data and plot it after your motion program has ended. Alex may or may not have mentioned this, but if you set up your gathering settings from the plot program, you need to actually hit gather stop one time in order for the settings to be downloaded. The settings are not automatically downloaded when you are changing the settings because they don't want to lag the program. They only send the gathering settings when you actually start gathering. So hit gather stop one time from the plot program, and then you can run your motion program, which executes the gather.enable equals 2, which is equivalent to clicking the gather.enable start button. And then at the end of the motion program, gather.enable equals 0 is the same as hitting the stop button. So this section of the presentation just goes through the process of uploading and plotting your data and scaling it and so forth. So you can take a look at that later for your reference if you want. But the main idea is just encapsulate gather.enable equal 2 in dwells to start the gathering before the relevant motion of your motion program, and then at the end, gather.enable equals 0 encapsulated in dwells will stop the gathering. That's the main idea. So now let me explain our final motion program and PLC exercises. I still want you guys to go back and do the first set of PLC exercises, but I want to explain this right now because I need to go work on something else. So this section of exercises you can do after you finish the first PLC exercises. This set of exercises incorporates both motion programs and PLCs. So the structure for this section is we'll show the exercise prompt and then a flow chart after that, which you can reference if you need a hint as to how to complete the exercise. And then at the end of all of these exercises, there's actually code solutions which you can go look at if you get stuck and need some help. So the first exercise is pretty simple. We want to index motor 1 to drive a fictitious lead screw a distance of 10 user units forward, pause for 4 seconds, and then move to its original location. And each of these moves should take place in 1 second. So this will be practice in setting up TM and TA to produce the motion in the amount of time that you want. And just to note, this is rather important, the default max speed and INV max settings in PMAC will probably not be good enough to achieve the kind of speeds we're asking. So you want to loosen the constraints on motorx.max speed and INVMAX in order to achieve the speeds we want. So for this exercise, you're pretending you have this hardware, 2,000 counts per revolution encoder, which actually you do have. We're pretending we have a 5-to-1 gear reduction and a 1 centimeter per revolution pitch lead screw, and you want to make sure you blend in this exercise. So whenever you have a gear reduction, you take the number of counts per rev and you multiply by the gear ratio before defining your axis definition statement. So we have 2,000 counts per rev times a 5-to-1 gear reduction. So you'll get 10,000 counts per user unit, which we're saying is centimeters in this case. And then your coordinate system definition can be &1 #1 points to 10,000 x. Then it'll represent 10,000 counts per centimeter. So that's the first exercise. This exercise can be completed with just a single motion program. This one doesn't actually need a PLC. And you can do it with whatever move mode you prefer, linear, spline, PVT, whatever you like, except for circle. Circle doesn't make a lot of sense in this case. And here's the flow chart in case you need a hint. The second exercise is similar, but it expands a little bit. So now you want your axis to move from 0 to 10 centimeters and then pause for 4 seconds, and then move to 20 centimeters over the course of 2 seconds, and then pause for 1 second. And then you want to return to 0 centimeters in 1.5 seconds. So this gives you practice in doing various move distances with various times. And then you want your programmed pauses to change with variable feed rate. So you remember the delay command can be used for pauses that scale with changing feed rate. So you want to use delay, not dwell. And then you want to create an auxiliary PLC that's monitoring an input switch. And when you flip the switch, you want to scale your coordinate system's feed rate down to 50%. So when the switch is on, you'll go to 50% feed rate, and when you turn the switch off, you go back to 100% feed rate. The way that you command 50% feed rate is by writing chordx.desTimebase equals sys.servoPeriod times 0.5. So it basically cuts your feed rate in half. And then you set it back to 100% by writing chordx.desTimebase equals sys.servoPeriod. Bring you back up to full speed. And then you probably need to increase your chordx.timebase slew in order to permit faster changes in the percent feed rate. So all of this part should be done in a secondary PLC that's running at the same time as the motion program. The third exercise is an exercise in calling motion programs from a PLC. So the previous two exercises didn't require this, but the third exercise requires that you write 2 motion programs. Motion program 1 will be called from the PLC if machine input 1 is on, and then your stage should move 0 to 10 centimeters at a certain speed, pause, and then return. If machine input 2 is on, you call a different motion program that moves a little differently, And then if both of them are on or neither are on, you do not call any. So you'll have one motion program monitoring the inputs, or sorry, you have one PLC monitoring the inputs and calling the appropriate motion program based on which input is on. So this exercise is done with one PLC and two motion programs. And there's the flow chart for you. The fourth exercise involves both an X and a Y axis. So up till now you were just using one axis. And in this motion program you want to quickly draw this shape. So it's basically just a box with a line through the diagonal. And you want to execute this whenever you press one of the tactile switches. So in a PLC you'll be monitoring the tactile switch, and when it's hit you will start gathering and run this program. And you want to disable blending for this by setting chordx.noblend equals 1, and that way you will cut the sharp corners. If you don't disable blending, then you'll make kind of this weird rounded box, which is not what you want. So this exercise uses one PLC and one motion program. The fifth exercise is a grab bag of move modes. So this one will allow you to practice using rapid and circle and PVT. So the idea is you home motors 1 through 4. So you can do home 1 ... 4 in your motion program. And then you use a rapid move to move your X, Y, Z axes to X5, Y2, Z1. You want to start jogging motor 4 by issuing jog plus 4. You want to cut a full circle using circle 1 mode in the XY plane. And I believe that this example actually forgets to tell you where the center point is, so you can just establish it wherever you want, really. I think the solution code puts the center point 1 unit in X to the left in the negative direction from the starting point. And then you want to use a PVT move to go to the endpoint X1, Y1, Z3 over the course of 1 second and an ending speed of 3 user units per second. And then once you reach that endpoint, you want to rapid to the origin and stop jogging motor 4. So we're pretending motor 4 is a spindle motor, so it's just kind of spinning as the other motors move in a coordinated manner. Something to note for this exercise, you can either put motor 4 in a different coordinate system than motors 1 through 3, or you can put it in the same coordinate system and assign it as the spindle axis in that coordinate system. So both ways will allow you to jog motor 4 independently of the motion of the other motors. And if you don't remember what the spindle axis is, you can look back to Alex's presentation from yesterday or today, where he discusses the spindle axis. The spindle assignment is, for example, hash 4 points to S, and then you can use that as a spindle and jog it as you desire. And the last, you have a plot here in case you want to compare your results to the solution. The last exercise teaches you how to use spline move. So in this exercise, you want to make a spline move with varying time in each of the sections of the spline. So the first section will be 200 milliseconds, second section is 300, and third section is 400 milliseconds, so that the entire move occupies 900 milliseconds, and you move your axis 1 user unit over that time. You can use whatever axis you want, X, Y, Z, or even A if you want, as long as you move 1 unit in 900 milliseconds with these sections, and you can compare to this plot if you want. And all of the solutions are given here in example code if you need to reference them. So I'll probably be here for a little bit, and then I need to leave in about 10 minutes to work on something else, and Greg will come down and help you guys. So any questions for me before I let you guys just have at it? Okay.